Okay, I think we have quite a handful of folks here. Good morning, everybody. Back to another Builder Forum series. Today's topic is Part 3 Energy Step Code, and this is a new topic for us, EV charging impacts, something we really wanted to get into and start figuring out how that really impacts our development and design. Our workshop today is brought to you by Focal Engineering, and that's Susan and Andy. And Susan's been around forever. She's a staple in all matters step code, zero carbon step code, design and implementation. She's remarkably credible, and we're lucky to have her today. Today's workshop, the Builder Forum series, and all things around that matters are brought to you by the Green Buildings Department. And that's Annie Zhang, our technical assistant, Jean Surendran, our building energy. Hey. So I want to say Happy New Year. It's almost spring, so something in between that. Last time we saw y'all folk was probably in October for those who joined us. So on our agenda, we're going to be talking about the last time we met, and that's in October, and we're going to have a recap of our last workshop, maybe some reminders as well. And then we're going to get right into the meat of the day. That's with Focal, talking about Part 3 step code and EV charging implications. I want to encourage everybody here to use the chat for questions. I think Susan might talk to it when she starts the slides. I'm not sure if she has a Q&A period or intervals, but either way, do use the chat and ask Susan questions, ask the township questions, ask each other questions. And I think that's really a key feature that we really wanted to promote here, the Builder Forum series. This is a forum. It's actually for everybody. So do if you're an architect, you have a question for another architect or electrical engineer, etc., please do use this chat function to do that. And as well, Susan will probably provide some instruction on how you can ask questions as well. We do prefer that they are answered or asked in the chat so we can keep the flow moving. And a reminder, as I noted right at the beginning of the meeting, please do turn off your AI note-taking software. We haven't still figured out how we can integrate that here, and we do have concerns around privacy, so we do appreciate turn it off. So a bit of a recap, and use the chat now if you were with us at the mechanical design workshop we had in October. This was in person in partnership with Maple Ridge. This was a real important workshop we had been working on for over a year, and we delivered this workshop to industry for absolutely free. As we recognize, the last many years, we've been really focused on step code and zero carbon step code and a lot of this really technical stuff, and that's great. But we wanted to zoom out for a second and say, whoa, let's go back to some of the basics and start asking each other and our builders and industry members at the Part 9 level, how much do you know about designing a mechanical system? How empowered are you in that part of the design process? Are you really relying on others to do that, or are you really kind of in there and optimizing your design and construction flow? So among many interesting things we learned at that workshop, and that's a picture. It was a full house. Many peers across the province attended. And amongst a few of those things that we learned there, we learned really how important right sizing is, how important coordinated design is, and what the impacts of not having a coordinated design can have on your project, and how to ensure your drawings and really even just your contracts are complete. How do you read a contract? How do you read a quote? How do you ensure you're comparing apples to apples, just oranges? If you missed it, do say something in the chat. We have a surprise for you a little bit later. And to illustrate some of the interesting things we learned there at our workshop through BCBC since 2012 or earlier, any kind of Part 9 residential construction, you do need to size your mechanical system to a standard. Not one of these kind of, well, the house is 3,000 square meters and I'll just kind of guesstimate it's going to be this many BTU, 100,000 BTU, or whatever folks used to do in the past, there's actually a methodology. And if you can see this thing on the right here, it's a rule of thumb versus using the standard methodology, which the township does require, and we check for, and it's a part of our building permit process. In the past, if you did use a rule of thumb, in the case of, for example, on the first kind of bars you see there, to size your heating equipment, this person this was a step 5 home actually. Has a few answers there, but they have a step 5 home using a rule of thumb, and they calculated about a 75,000 BTU burner or boiler or furnace. 75,000 BTU. It's pretty big, maybe standard. And for cooling, it was something like 82,000. A high cooling load. So when they use the real methodology to size these systems, and you can guess here. So if that's 75, what do you think? Is it 10% less or 20% less or whatever it is, or is it roughly the same? I don't know. You can guess. You can do that in your head if you like, or put it in the chat. But I'll make the big reveal here, using the methodology which is required in British Columbia for a building permit. In this step 5 home, it was probably less than half. The actual right size for that building was less than half for both the heating and cooling portions. And this has a huge impact on how you actually design your system, and as well, probably how much it costs. So do take a look at that course, or do ask us more about it. It's very, this kind of information for your design and construction process can really be an important part of how much, how things are designed and really how much they cost. If you did miss this, you have a treat. I want to remind you of our Green Buildings on Demand. So today's lecture is brought to you by our Building Forum series. We recognize not everybody can be here at the exact same time in the exact same place. So we have an online platform which we call Green Buildings on Demand. It is on demand. Use it when you like. It's free. You can watch any course, including the one that Susan's putting on today with Andy. For those who are not here, you can watch your course at any time and still get the credits, which is a first of its kind, certainly for free in British Columbia. A few stats here. We have over 300 users through Building Forum series and GBD. We put around 10,000 credits for free back into industry. No, probably, I don't know, 15 courses or more. We have a variety of new resources I'd like to share with you, so do play around on that page. For those who are in Part 9 construction, design and construction, we have a very cool in-detailed report by one of our previous researchers, and the question she wanted to answer was, do heat pumps work in British Columbia? Do they work alone? Need supplementary heat? In mid-BC or all the way up to northern BC. And she ran a number of simulations using actual heat pump specification data. This is not from a textbook. This is not from a university course. This is going to Mitsubishi and getting their makes and models and getting their performance logs and translating that. Are very interesting, sometimes shocking, sometimes motivating. I do recommend you go to our resources page and do read that report. It is a real monster. Susan's lecture today comes with a very in-detailed study. The time she has today is not enough to go over everything. All of the details here are in her report, Part 3, Step Code and EV Impacts, and it's in our resources page. We have other interesting reports to review as well. And for those of you who did miss the in-person mechanical design workshop world, or you're looking to brand out in the Part 9 world, you missed our workshop. Yes, we usually put the videos on and you can watch the videos. Our workshop was more of a one of its kind, where it wasn't just a workshop where you're listening and taking notes. We had activities. We had exercises. We had opportunities to talk with our peers at the table and to work through worksheets and work through problems together. And we really wanted to bring that experience throughout the province. But how do you do that on a website? So Annie did the lion's share of work on this, along with a lot of help from Jean, to translate an in-person live workshop with exercises and worksheets and drawings and all this stuff and translate that into a digital take-home experience. and on our website. And I believe, Annie, if you could just nod, it is live. It's accessible to everybody. There, she's nodding. So we have everybody has access to that workshop where you can watch videos, be tested, have the opportunity to play around with the exercises, all available today. I think you get 4.5 credits if you complete the whole thing. I'm sure it's a first of its kind in BC, certainly for free. Do take a look at that when you do have the time. Okay, with all of that, I think we're ready to move on to the next part. Oh no, we're not. Before we move on, I've highlighted that we do have this exciting course available to everybody. However, it is brand new. It's not something you press play and you sit back and you watch. There's a lot of stuff to be done and to set you off kind of right in the right direction. I'm going to call on Annie just to give us a quick, brief demo on what the course is and how it really works, just so you don't get stumbled up too much and kind of get a little bit frustrated with this new format of exercise. So Annie, I'll pass it to you. You can.
Thanks, Kevin. So I could just quickly share my screen so that everyone can see me doing the demo. Can you see my screen? Right.
Yeah,
so this is the homepage of our online learning platform. So as Kevin said, we do have a resource center, so where you can find all the cool reports. So including today's topic, you can find it over here. And then we also have some like scholar report, and then you can find it over here. And then back to all the courses where you can see all our courses. So after today, we have 19 courses in total, and all of them are totally free, and then you don't need to pay anything, and then just you can earn the credit totally online at your own speed. So this is the latest, the newest course we just published this week. So it is developed based on last year 2025 in-person mechanical workshop. So if you click enroll for free for credit, and you will see the course show on your dashboard. Just click this, and you will see the basic introduction, and you're gonna watch some video and the presentation video. And then we also have some worksheet that you need to download and keep it open when watching the video and then completing the quiz. So after download this, you just complete the video and then complete the quiz. So you can just stop anywhere, any path, like do it at your own speed. So this is totally online. So you can earn credit like when you finish this. So you will receive a certificate at the end when you complete all the video and all the quizzes. Great. So Kevin, I will get back to you. Do you want to continue?
Thanks, Annie. So as you can see, this course is much more involved and engaging than anything we put out there before, and really it's meant to help you kind of download the content, the information, the education a little bit more deeply, so then you can of course practice that in your work. So right before I pass it off or introduce Susan and Annie and Andy and let them take over for the day, I do want to I should have started this at the beginning of the lecture, but I'll do it now. I do want to start the meeting in a good way, and I want to acknowledge that the Township of Langley acknowledges the traditional territories of the Coast Salish peoples, and in particular acknowledges our valued relationships with the Katzie, Kwetlan, Matsqui, and Semiahmoo First Nations. With that, allow me to introduce our speakers, Susan, Andy, and maybe some backup from Jeff from Focal Engineering and AES. Susan, as noted, she's a mechanical engineer and the CEO of Focal Engineering. She brings decades of experience in modeling, design. She's a regular educator on behalf of the township, but also the province of BC. She's a real superstar. Everybody knows her, and probably one of the most credible in the field. And he's a mechanical engineer with Focal, has decades of experience bridging energy efficient, low carbon design in buildings all across BC. A real resource here, so please put him to work, ask him questions, and use these resources wisely today. So thanks, Susan and Andy, for joining us today. And everybody, let's join me in welcoming our speakers for today.
Thank you so much, Kevin, and everyone for the warm welcome, and thanks for having us today. I'm just sharing my slides, so hopefully everyone can see those and hear me okay. Let me know if there are any issues. Thanks, Kevin. I always, appreciate an introduction that highlights my gray hairs. And I just wanted to say to you a big thank you to the township for hosting not just these sessions, but the workshop that you're doing. It's really great to see such a huge community coming together, not just for education, but as you said, as a forum. And so we've designed this and got some slides in here that hopefully will pull this group, this great amount of brains that we have in this virtual space right now. So we're really looking forward to sharing today's topic with you and hearing your feedback. So as Kevin has introduced, today we're going to be talking about impacts on Part 3 buildings of the upper step code, both energy and zero carbon step code, and electric vehicles. And so we do have myself, my business partner, Andy Chong, who's brand new to Focal, but got, as Kevin said, decades of experience with the industry, and also Jeff Halpney from AES Engineering, who participated on some of the electrical side of this analysis. As Annie mentioned, our full report for this study is available on the township website, but we're just going to be going through some of the highlights today, and we can answer some more questions about the study if desired. So building on Kevin's land acknowledgement, this particular project was for the township, and so on the traditional territories of the Coast Salish people. Andy and I are calling in from the ancestral territories of the Lekwungen speaking peoples here in what we call today Victoria, BC. And that includes the Esquimalt, Wasanich, and Songhees First Nations. And for those of you who might be planning a visit to Victoria, our company once did a tour in the downtown Inner Harbor by the Songhees First Nations, and they took us around all the spindle whorls and told us the history of the place, and it was really fascinating. So if that's your jam, I highly recommend coming and checking it out and learning from them a little bit more about the past of these beautiful lands that we're privileged to live, work, and play on. So a little bit of an overview of what we'll be talking about today. We want to just give you the basis for the original analysis that we were working on with Langley this past year. So we will talk a little bit of the methodology for analysis, because that does help provide some grounding in the results that we will be sharing. And then we really want to share the key findings around energy and emissions, cost impacts of these upper steps, anticipated impacts to mechanical and electrical design, and then getting into that peak demand, electrical demand, and EV charging that Kevin was mentioning. Throughout this, we do have the Teams Q&A set up, so please feel free to pop questions in there and we'll try to respond to them, whoever's not speaking. Or we can also address them at the end. We do have a fair bit of time slotted for the end of today so that we can have a group discussion as necessary. And we're also going to be running some sort of less formal but poll sessions where we can basically get some of your feedback either on the information that we're presenting or getting some gut checks. And the first one that we wanted to start with was just getting a sense of who's in the room with us today. And so I've just popped in the chat a link to this poll that we use. It's called Poll Everywhere. But when you click on that link, what you should see is this. Oh, sorry, when I pull it over, you can't see it because the slides are in front, but basically a black screen. I see a bunch of folks are figuring it out already. That's great. Basically, if you put the pollev.com/FENG604, you're able to respond to our poll questions and they will just update as we go along. So you don't need to do anything other than that. Enter that into an email browser if you have one. So we're just trying to get a sense. It looks like we've got a lot of Part 3 design consultants, wonderful, some government representatives as well, and a variety of other folks in the room today, so that's great. I'm going to leave that open. You can keep responding, but we'll move along to the next slide for now. Okay, so starting with our project overview. The initial request from the township was for an analysis looking at these 3 key questions. as the step code higher tiers are approached, how are we expecting buildings to change and what kind of things can we plan for? I just want to have a quick comment that I'm using the word higher tiers to represent both energy steps and zero carbon levels. So I'm not trying to confuse this at all with NECB tiers if you're living in the modeling world with us. It's just kind of a word that we're trying to use to represent both energy steps and the zero carbon levels. So how are we basically expecting buildings to change and adapt as they have to hit these higher tiers? Building on top of that, how might EV readiness requirements impact peak electrical demand? And then taking that information, the township is really looking at how can they help set up higher step code buildings for success. And knowing that these higher levels are coming, what are things that can be done today to really prepare the township for those things and make it as easy as possible on builders, developers, and project teams. And we were asked to focus this study in 5 main areas. So one being architectural and envelope design and looking a little bit at the aesthetics of the building and what planners might be expecting to see change from the exterior. And then there was a piece on mechanical systems, and that has a couple of different elements, which Andy's going to be getting into. And a big part of this was capital costs. We wanted to look at options and design features that would be reasonable as far as the capital cost goes. And so we worked with AIBC Group, professional quantity surveyors, to help cost all of the design measures that we were looking at. And then the peak electrical demand from the assessment, as well as the EV charging infrastructure and the input that we were getting from AES engineering. So those were kind of the 5 key areas that we were looking with under the study, and that we'll be presenting results on in a little bit. And just a bit more context so that we're all on the same page. The Township of Langley currently has certain step code requirements beyond the provincial minimums. And so we've listed these here in the in this table. The key one, I think, is really the residential being energy step 3. And we noted that also covers group C occupancy, includes also hotel and motel. And then office business are step 2, which is currently the provincial minimum. And this is available at the link on their website that we've just put underneath the table. This residential step 3 was as of January 2023. So just a note that a lot of our comparisons were based on comparing versus this minimum requirement in Langley, because this is a Langley specific study. But at a few times we do compare against the base 2 step code across the province, just because that gives you a little bit more context outside of Langley as well. So our methodology, as per the study request, was to use energy modeling to assess a number of different archetypes under these lower and higher step code tiers. And so for the first phase, we worked with the township to identify some archetypes, and they wanted us to look at 4 representative buildings. So there's a low-rise MURB, a high-rise MURB, an office, and a retail, and we'll give you a little bit more detail on those in a few moments. Phase 2, we worked with the township again to figure out what design features of these 4 archetypes should we be varying to go from a sort of typical base step code building to an upper tier building. And so we chose a number of key inputs, and then we varied about 30 of those to get these combination of kind of lower step buildings and upper step, which resulted in about 7,500 iterations and simulations that we did some parametric analysis on. And concurrently, this is when our friends at AES were doing these EV peak load calculations that would also inform the study. So because we wanted to look at how much does a lower tier building cost versus a higher tier building, we then had to work with AIBC Group to try to price out what is the difference in costs for each of those measures. And so they helped us provide Class D costing for some of those design features that we were working on. And finally, we did our results analysis in our report where we took all of these iterations and a lot of the study focused on these lowest cost results. So if projects are going to have to meet step 4, EL4, how do they get there with the lowest capital cost based on the measures that we were iterating? And then the other thing that we were looking for was trends across the results. So do we see common design features showing up really quickly as buildings are starting to transition from the lower steps to the upper ones? So giving you a quick overview on the building archetypes that we were working with. This is the mid-rise MERB, which is a really common one in the township. So it's a 6-story building, and this is based on some actual anonymized floor plans that the township provided us. So you can see one level of it represented in the energy model shown on your screen there. And because of the step code requirements, as we mentioned, the base step or the lower step for residential in the township right now is step 3 and upper is step 4. And we assessed all 0 carbon step code levels from EL1 to 4. We also looked at a high-rise MERB. Now, the township did mention this is a little bit less common for them at the moment, but it's still valid because it's can be one of the harder archetypes to achieve upper steps with, especially for the energy step code. So this was a 40-story building, again, based on some floor plans that you can see with a lower step of step 3, upper of step 4, and full 0 carbon step code analyzed. Then we had a 1-story strip mall, and you can see it's based on a number of different size CRUs. This has slightly different steps, lower step 2, upper step 3. We had a 5-story office, again with lower step 2, upper step 3, and all 0 carbon step code levels. And for the office building, this was where we were asked to start building in the impact of EV charging. And so the questions that we had to look at were if the 10, 25, and 45% of the required parking stalls are made EV ready, how does that impact the electrical load on the building? And there was a 5th building in there. We weren't asked to model an industrial building. However, again, we were asked to look at the impact of EV charging stalls for industry. So that was a separate exercise that we did, but then built this into our analysis. So as I mentioned, for each of these building types, we selected some key design features in these sort of 5 areas, and we varied roughly 30 of them between some lower and some higher values. Now, not all variations are applicable to each archetype. So for example, we varied the type of corridor makeup area unit, but that is only applicable to the residential, the MERB buildings. So some of the things were static. We looked at occupancy, weather files, etc. But some of the items that we varied were the envelope systems, the mechanical systems, and that's sort of what we'll be talking a little bit more about today. Some of those design features that basically design consultants have the opportunity to impact. As I mentioned, yes, this resulted in roughly 7,500 iterations, and we built out a parametric tool so that the township can keep using these afterwards and keep querying that data set for questions and doing some data mining later within the context of this analysis. Okay, I'm going to do a quick jump into costing before we get into the findings from the analysis. So one of the things we realized as we got into the study is that while we're looking at incremental costs between lower and higher buildings, or lower and higher step code buildings, it's really most valuable if we could present these results as a percentage of overall base cost. But we were not able to price out these buildings in their entirety. And so what we used was the 2025 Altus Cost Guide to try to establish a base cost for these typical types of building. So if I just grab my pointer here, for example, if we look at the mid-rise MERB and you look at the Altus cost guide for Vancouver from 2025, it said that on average, or sorry, the range of low-rise wood frame MERBs went from $275 to $365 per square foot. So for our 6-story, 85,000 square foot building, this would be an average construction cost of $23.4 million. And so we built out those base costs for our 4 building types. Obviously, this is, one data source, and we just took the middle number, the average between the low and the high, to establish this base cost. So a lot of our analysis was sort of looking to the percentage increase over the base cost. And so we wanted to ask this group a question about whether you think these costs are reasonable if you have experience and background in that sector. So I'm going to take a little speaking break for a second and ask everyone here if you can respond to the next poll. What are your thoughts on those cost ranges that we saw from the Altus guide? So I've put them here again, just so you can see, and you don't have to flip back and forth between slides. Are these reasonable ranges? If you have mid-rise MERB expertise, is that what you would expect to see? Or, oops, sorry, I scrolled the wrong way. Or I'm getting some comments here that one says a couple office too low, a couple office too high. It looks like the mid-rise MERB is too low, so that's actually some good feedback. And then we have a bunch of folks who's it's not their area of expertise. That is totally legit. Thank you for letting us know. We're just trying to, get a little bit of brain hive feedback here.
I'll just add some color commentary. Hello, everyone.
Please do.
When Susan shared these numbers with me, I did a double take myself personally. So I've cast my own vote. I think it's fascinating here, and I just want to remind everyone of our qualifier. This is not our opinion. This is from a very credible third-party Altus cost guide, right? So I've formed my own opinion on too high, too low on some of these, but I'm really fascinated to see if that resonates with others.
Yeah, thanks, Andy. And just I don't know if you guys can see this on your screen. Because I'm presenting, the functions are a little bit different, but there's a see more option down there too, if you hover over it, so you can vote on the retail side of things. Okay, thank you for those who are providing feedback. I'm going to keep going, but that slide again will stay up for a little bit if you have other thoughts. And honestly, if you have anything you want to throw into the chat, please do, because I am actually quite curious as to how these are landing with folks. Okay, so the last piece of the costing that I just want to explain for this study was that we needed to really think through how to develop some unit costing, because as I mentioned, 7,500 design iterations, we could not cost each of those individually. So what we had to do was go back and say, for example, on the window side of things, if we have a double glaze system versus a triple glaze system, can we figure out what the unit cost is per meter squared for each window type, and then multiply that rate out for the window area? And so we worked with advocates to do this for the envelope systems, windows, a variety of HVAC heating and cooling systems. For the residential, we did this for corridor ventilation. We broke out HVAC ventilation from heating and cooling so that we could have HRVs and different variety of heat recovery performance, and then also domestic hot water systems. And so within our parametric analysis, we were able to say, okay, for this building type, based on the measures, or you might say ECMs that we have involved in this one simulation, we could build up the incremental cost for that simulation and then compare it to those base building costs we were looking at and try to get a sense of how much more are we anticipating capital cost wise in order to achieve these upper steps. So that gives you a pretty quick summary of our of our methodology. And now into the maybe fun part, the finding side of things. And just a reminder that we're looking at those sort of from the perspective of the 5 key areas that we were asked to. So starting with architectural and envelope, I think probably it's not a surprise to a lot of the people we saw on the call, especially those Part 3 design consultants who've been working in this area, that some of the least expensive ways to get to the upper step code tiers was through simpler building form and lower glazing percentage. So this can, the simpler building form, instead of having a very articulated building, you have more compact, and that results in a lower envelope area or enclosure area, which just means less money. You're not building as large of a building. And then the lower glazing percentage is also fairly intuitive because windows cost more per square foot than a typical wall would. And so by reducing the window to wall ratio to a manageable size, then you're not only having a better overall insulated building because walls are better insulated than windows, but they also cost less per square foot. Now, of course, there are impacts to the building operation for this. So, there can be interior daylighting reductions if you are reducing your window to wall area. And one of the things the planning team was kind of interested in was the exterior aesthetics. As we have smaller windows, you're going to get less of this sort of overall glazed look. Manageable, but just something to kind of expect down the road. Sorry, my pointer's gone a little funny on me. Another thing that we were looking at, and this was of particular interest to the township as well. I know they've done a lot of work at looking at overheating as one of the sort of warmest places in Canada, really, is lower solar heat gain coefficient glass. So this could be achieved quite, again, with a very low cost. And it reduces the peak temperatures and just the overheating hours that are experienced in suites. And as this 26-degree requirement has come into the BCBC for at least one space in the suite, I think Andy will be touching a little bit on that later. We're seeing more cooling requirements and more cooling energy. So having this kind of reduction does show benefits.
Susan, if I can chime in now, though, actually.
Sure, yeah, even better.
I'm chomping at the bit. I think it's really important to emphasize the importance that, high solar heat gain coefficient is not better and low solar heat gain coefficient is not better. I think in the past, we've stereotyped this parameter in building envelope design as, more solar gain equals bad. And I think as the industry has come around, become more sophisticated, the truth is that it depends. It depends on the exposure, and it depends on the building type, and it depends on which limbo bar we're trying to clear in this new framework of step code metrics. Very simply, I think a higher solar heat gain coefficient means more solar heat comes in. That's a good thing for us in the winter. We do live in a heating dominant climate. It is cold for more hours in the year, despite living in a very beautiful part of BC. And so that actually helps that Teddy figure, which we'll get a little bit deeper into later in the presentation. But that actually helps us achieve the energy step code, having lighter, clearer glass, because we're getting that free solar heat. But that's in tension with this new issue that we're getting a lot more news coverage and presence of mind on, which is the impact of overheating, especially in buildings that don't have active mechanical cooling systems. So in the summer, relatively shorter period, fewer proportion of hours of the year where this is an issue, but lower solar heat gain coefficient reduces that unwanted solar gain in the summer, in the cooling period. And so it's not really you can't paint them with one brush. It's a matter of optimizing that one fixed variable that's very difficult to change, obviously, for what serves the building best over the annual performance of the building. And again, that limbo bar, what keeps us under the Teddy metric, which is an obligation for step code.
Great points, Andy. And yeah, I think the finding from this one was specific to that. What are cost-effective ways that we might see people addressing these upper step code tiers. But you set me up beautifully for the next point, which is another thing we might see is more shading options. Because as Andy said, it's great if you can let in passive heat gains in the wintertime and then just block them and shade them in the summer when they're unwanted. So the darker glass might be a cheaper way of doing it, but for projects that have the budget and or the interest, things like exterior blinds, which are less common these days in North America, but we are seeing an uptick in, are something that we can start to expect to see more of, hopefully. And that's kind of actually the visual that we've got on the left there. That's actually a picture I took of the Olympic Village many years ago with all the blinds down. And the last one that we just wanted to prepare people for, and this is again more from an aesthetic planning side of view, is, you know, just the thicker walls, improve performance by having greater insulation. Ideally, windows should be inset into the walls a bit more so that the windows are mounted along the insulation area. And so this could have a little bit of an impact on aesthetics from an exterior perspective that people could be aware of. And occasionally the thicker walls can have some FSR impact too, especially on smaller lots that are trying to build like right to the property line. So there were more findings that we had in the study, but these were sort of some of the key things that we were seeing occur most frequently in the lower cost results for upper tiers. We also wanted to show a few examples of where these are actually being used. So this is a project from the township itself. They provided with a MURB with a 23% window to wall ratio. And so you can see that even that sort of lower percentage is not, it doesn't seem visually striking as low, at least from the outside. And just from our perspective, a lot of the projects that we're working on focal wise for a lot of mid-rise projects these days are around the 20 to 25% window to wall ratio. So we're not seeing that as too uncommon, at least in the mid-rise size of things. We're also working on some projects, some high-rise projects that have lower window to wall ratio, still higher than the mid-rise. But here's an example. We're working on 3 towers in a different jurisdiction, but gives you a sense. And they are 34 to 48 stories and on average 35% window to wall ratio. So here's just a picture of the energy model of the 48-story. It's going to be hitting step 3. And oh, sorry, there's a typo there. It's not 2% window to wall, it's 32%. And you know, these are real projects. So this building is not complete yet, but it is under construction. And the other project example we wanted to share was some with exterior shading and how this geometry can kind of look. This is a mid-rise MURB that we've worked on Vancouver Island, and it just has the whole gamut of overhang, shades, fins. It also uses angled facades. It's a little bit harder to see, but because of the orientation, it's kind of an L-shaped, but not at a 90-degree angle. It's a sort of wider gap than that. And so some of the facades were angled so that the solar gains could be managed a little bit more on the south facade. So some really thoughtful design went into this one here. And then we also just wanted to encourage folks to kind of think outside the box with some of these architectural and envelope ideas. And so we wanted to share this one step 4 project. This is a real project we've been working on, and it was having problems hitting the Teddy limit of 15 for step 4 residential, which can be quite challenging. It was already well insulated. It had good double glazed windows, good heat recovery, and a strong air tightness performance. And we were working with a very wise developer who didn't want to just drop the air tightness rate and say, oh, we'll kick that can down the road and get a really good air tightness test. And so as a project team, we looked at a variety of solutions for the specific project and said, well, what if we go to triple glazed windows? That's about 100 gram premium for this project, and there's an additional benefit of sound attenuation because of the extra pane of glass. We also looked at adding an inch of exterior wall insulation, and that was going to be around $60,000. But like I mentioned, this is one of those projects on a small lot, and it was going to be a bit of an FSR issue to add more floor area to the building. And then another option we looked at was, well, what if the contractor hires a site person for a year whose job it is to monitor the air barrier so that we get that air tightness test result that we are looking for that will help us achieve the TEDI. And that was estimated at $54,000-ish. So I'm not saying that either solution is right or wrong. Of course, it's very project dependent, but it was an interesting exercise in looking at what are the levers that we can pull to get to those upper steps, and what is the most cost effective, and how are we going to achieve it for this specific project? Oh, and I forgot to mention too, we were doing some embodied carbon analysis on that project, and so adding the extra inch of insulation added a lot to the embodied carbon. And so, just having someone on site making sure that there aren't huge holes left in the air barrier as things progress was a great way to get to the step 4 TEDI without adding embodied carbon. So wrapping up the architectural envelope side of things, we're just curious again to poll folks based on the kind of top solutions that we saw to achieve step code or these upper tiers. Can you see yourselves using any of these strategies on your next project in Langley? And you are able to select multiple choices. So if you think that, lower percentage glazing and shading makes sense, then please feel free to select multiple. Interesting. The two I just happened to throw out there are the ones sort of in the lead. It seems like a lot of folks are saying, the lower glazing, which makes sense cost-wise, and also more insulation, thicker walls.
Hey, Susan,
Yeah.
at least in the chat that I'm looking at here, I don't see the link.
Oh, here, let me repost that.
I see Heather is the last person that made a comment. Oh, there's, okay, all right. Thanks, Susan.
Yeah, no problem. And Heather, to your point, I was just, I'm not an expert in FSR calculations. It was mostly it was something pointed out by the architect for that particular project that adding the insulation was going to be a challenge to the FSR calculation. I'm sorry, I wasn't personally working on that one, so I don't know exactly to the extent, but that was the architect's response to that particular one. Great. Well, it's good to see that a lot of folks are interested in adding more insulation, because that's ultimately the way to keep our buildings warm in the winter and cooler in the summer, right? Is by keeping the hotter temperatures out. We're going to switch gears a little bit now, and I'll hand things over to Andy to talk about some of the mechanical findings and strategies moving ahead. But that envelope poll does stay open for a little bit longer if you are still responding to those questions.
Okay, thanks, Susan. And good morning, everyone. Thanks for being here and your time. I suppose now's my chance to say, go Canada, go. I think our women are taking the ice for the gold medal game in a few minutes, so we will try to not dawdle here in case anyone's trying to watch that on their other screen. I suppose at the high level, my role in this presentation is to answer the question, what are the mechanical implications of adopting these higher steps in both the energy and the zero carbon step code. And so where I want to start first is some observations before I draw any conclusions. I think the first that we've seen now that the step code has been adopted by many municipalities all over the province, we are seeing consistently that for most building types, TEDI, TEDI, is the more challenging metric to meet. Susan spoke about that in that focal project example from the island. It's true through all of the projects that I have touched, and it's true across project archetypes, from multifamily, single-family homes even, and commercial buildings. So while the energy step code and the zero carbon step code are aligned, they do have different implications on how new buildings adapt to each, because that TEDI factor is affected with mechanical systems that affect obviously energy performance, but the zero carbon step code is really about reducing emissions. It's not about necessarily optimizing the efficiency of the equipment and the systems that we're putting in our buildings. So yes, more efficient equipment helps. So for, apples to apples, an all electric inefficient building compared to an all electric very efficient building, yeah, the more efficient one is going to emit less carbon associated with that electrical consumption. But the real driver here, and I'm probably preaching to the choir, the real driver is how carbon intensive the primary fuel type is. And so we've all heard the BC grid, electrical grid is very clean, relatively speaking. There's lots of, ifs, ands, or buts associated with that. I'm not going to get into the politics and trading energy across the border and things like that. But when we compare it on paper, according to the modeling guidelines that are used to enforce these standards, electricity is 17 times less carbon intensive than the same input kilowatt hour or gigajoule of natural gas. And that's really where we have the strongest leverage in selecting our mechanical strategies that go into a project. So I will also underline, I'm not here to demonize natural gas. Natural gas is still okay. And I want to be clear, decarbonizing our buildings is not an outright ban on fossil fuels. It just means we have to apply them more intelligently. We can't just brute force with gas as the primary fuel input. So relocating it largely to peaking and standby roles. Okay, next slide. So what this means for energy is we are already implementing heat recovery ventilators in residential suites, almost as a prerequisite. It's a given. Any kind of residential building, we're seeing HRVs at the suite level, whether it's central or decentralized. That is already necessary to meet the lower steps of step code, which Langley is beyond. Where buildings, I believe, need to look next to meet these more stringent TEDI targets is applying heat recovery ventilators to other parts of the building where we were not de facto going to HRVs. More on that in a moment. I'm going to speak about that very specifically. For carbon, it means, like I said, steering our heating equipment towards electricity as the primary fuel source. It doesn't have to be the be-all, end-all. It is allowed to be applied in a hybrid or a dual fuel strategy, but we do need to look at these very capable, very market-ready electric products, including a wide variety of heat pumps. And we need to be looking at using those in buildings that are currently using gas for those end uses. So I loved to hear about that residential workshop. I was not part of that at the time, but I think that concept of right sizing our systems is huge. When we are plugged into a pipe with unlimited capacity, practically speaking, for burning gas and getting as much heat at a very high temperature as we want, we have had the luxury of not having to really fine tune and sharpen our pencil when we're sizing these systems. When we go to heat pumps that are a little bit more complicated and they are more sensitive to our outdoor temperature conditions, we need to be looking at right sizing those systems. And it's a more sophisticated design requirement than just throwing, gas equipment at the problem. Of course, when we are moving to electric means, many times this means heat pumps, like I said, but to that end, I think a really important end use of energy in our buildings that we have overlooked and misunderstood is domestic water heating. I will unpack that as well, but it is a major end use, especially in residential buildings and multifamily. And I am seeing a myriad of new equipment and tools coming to light that are perfect for that application and allow us to satisfy that building use with electricity. So going back to TEDI, next slide.
Can I jump in quickly on that,
oh yeah,
that heat pump right sizing topic? The reason for this picture too was it's, right sizing is importantly, and also considering location for easy maintenance of heat pumps and that kind of thing as well. Because we've seen some buildings with heat pumps on balconies, which can be great. But, the higher you go, you have to think about things like kids climbing on them and not making sure there's no fall hazard and how much space are you taking up. And then this was an example where we saw of heat pumps being installed outside of a balcony, but are there maintenance questions and accessibility? Where are the filters? How are they changed? And so when we were being asked to look at potential impacts to the aesthetics of the building, that kind of came up as where are you actually going to be locating these units, and how is that going to impact the operation and maintenance and accessibility of them? So just a note on that picture specifically.
Great point, Susan. And I'll also say our opinion is not that split heat pump mounted on the wall is an ideal solution. I love ducts and pipes, and I even think that's a bit ugly, but
It's
beauty in
an
the eye of the
honest
beholder,
building,
I guess. Susan, while you were chiming in there, I just noticed there's a really detailed question in here. I think we won't answer it right away, but maybe you can chew on. I'll just read it for everyone. It says, I'm curious to know if or how increased ventilation for the purpose of building pressurization was accounted for in the analysis. This is particularly a problem on high-rise construction. There's a little bit more to it, but maybe we can come back around, Susan, since you were very close to the modeling approach on this.
Great, thanks for highlighting that.
Okay, so on the next slide about Teddy, at risk of maybe beating this to death, probably many people on this call are painfully aware of what this means, but just as a quick level set, Teddy thermal energy demand intensity is literally the amount of useful heat that is delivered to the space to keep it warm over an average year. And it does include the ventilation air. The reason I think this is so important to clarify is it doesn't matter how efficiently you deliver that useful heat. If I use a fancy geothermal system, if I use heat recovery from a data center or a grocery store or whatever, I can throw a really complex, super high efficient, beautiful, fun to talk about system, and Teddy does not care. This is about the amount of useful heat delivered to the space. And so it's largely a measure of some of the aspects Susan already covered: building enclosure, air tightness, minimizing our heat losses to thermal conduction and air tightness. But the one lever that mechanical systems do impact here, which is a bit of a caveat to what I said, mechanical system efficiency doesn't really move this. Because Teddy is counting input useful energy, if we can reduce the amount of energy we need to heat the incoming ventilation air by recirculating, or not recirculating, by recovering waste heat in our outgoing exhaust air, that's heat recovery ventilation. If we can reduce the amount of ventilation heating, that is the trigger. That is how mechanical systems can have a very significant impact on Teddy. And so that's the reason why I advocated for applying HRVs in areas where we weren't previously considering. And I think that kind of relates to that question I read in the chat about corridor pressurization. And it also means looking at, okay, we already had HRVs in all these suites, blah, blah, blah. We know how to do it, bulkheads or central or smoke dampers and whatever, pick your poison. But are we using the best modern products out there? And as a very quick anecdote, there was a project I was involved in a few years ago here in Victoria, where a client was struggling to say, I can't believe we need to trigger triple pane glass on this building. It doesn't feel like it makes sense. It's not that cold here in Victoria. I haven't had to do it anywhere else. Why are we up against this cost issue? And through a pretty quick energy model, we demonstrated, hey, you guys are sourcing like run-of-the-mill, frankly, low-end HRVs. They are, a dime a dozen, maybe not a dime a dozen, but $200 a suite. There is one with the exact same form factor from another manufacturer, same input voltage, same electrical connections, same control, same duct sizes, everything. And it is 85% efficient. And yeah, it's more expensive, but it's like $300 instead of $200. Like, take that. That's the low-hanging fruit. There's the lever. The amount of reduction on Teddy as a result of making that HRV swap was more than enough to keep the double pane glass. And so I think this brute force kind of like, we got to throw everything at the wall and see what sticks to get to these higher steps. It's not the case. There are like very subtle, frankly boring to talk about swap outs that we can be looking at in our already conventional mechanical systems today that can get us there. This is not an impossible target, but if we take for granted that we're using the same strategies as before and not looking under a few new rocks to see, has the technology changed? Are there higher quality products out there? Then we're doing ourselves a disservice. Now about that corridor ventilation, Susan, maybe you can back me up on the modeling piece, but something I'd like to pitch out here, and it's not for everyone, but pressurizing corridors is it's a huge energy penalty. I'm not suggesting that it's not worth doing. I'm not suggesting that I completely understand the indoor air quality benefit of putting more air in than you take out, but it is an energy penalty because what it means in these multifamily buildings, especially high rises, especially mid rises with double loaded corridors, it means that you're putting energy into air that you never get back. Right. And so we're putting all this work in, like I said, smoke dampers or bulkheads or access panels or whatever you're doing with HRVs in your residential areas. We're putting all that work in for the ventilation that's constant in our residential suites. But then we're throwing like thousands of CFM at a time into our corridors and common areas, and it leaks out the building and goes somewhere, and we get none of that heat back. And so, it feels a little bit silly to a point when we are throwing like, the best and the most expensive HRVs at the residential areas. And then we've just kind of been blind to the source of energy loss, a big penalty on Teddy in the common areas, in the lobbies, in frankly, like the garbage rooms, right? So there are ways where we can inject air, we can have it positively pressurize the corridor, but it can migrate to another part of the building that needs to be exhausted anyways. Can we draw that out from the garbage chute? Can we draw that out from the waste room? Can we let it trickle down, a main circulation stair or something like that, and grab it out of another area of the building that needed to be exhausted continuously anyway? So I think some of these thoughtful approaches to, can we pair some of these areas that want positive pressure and want negative pressure, and can we marry them together to get heat recovery applied in areas we weren't thinking about previously? I think it's a low-hanging fruit. We needed to run ducts to those places anyways. We needed a supply fan, we needed an exhaust fan. Looking at HRVs is a very simple way of improving our efficiency in those areas and getting under that more stringent Teddy target.
Yeah, Andy, can I jump in there on that one?
Yes, yeah.
We have seen that a lot on low rise, especially because, you're not running as much duct work as you would for a high rise. We have had some projects that have looked at smaller HRVs for each corridor. This is when the corridor is not just a central one, but has some sort of exterior wall somewhere. And so there's just like a small HRV going through the corridor at each level, just to provide ventilation, a little bit of pressurization. And yeah, I think it's a good one, and that was definitely an area of study that we were looking at, is trying to reduce the heat loss for that. The step code is still a bit unusual because it allows the corridor adjustment for pressurization, and so it does skew the results a little bit when the adjustment is applied. It makes it very building specific based on the CFM per door that's being used.
Great, thanks. So next slide, and I'll just finish my point on HRVs. I just want to emphasize that second piece of how much better HRVs are getting. They are, from my perspective, they're pretty dumb pieces of equipment. It's two fans and a heat exchanger. So there isn't that much to improve on the fans. They're just pumping air through. It's two ducts crossing over each other. What has really improved is the form factor that these are coming in. Manufacturers are finding more and more creative ways to cram these into smaller spaces and actually maximize the surface area for heat transfer. The second area is the core technology. And so I would encourage you to not gloss over and think, yeah, they're all the same. It's an aluminum core. And, 2 years into this, it's not my problem anymore. Someone else is going to have to deal with it getting clogged up with cat hair or whatever. There is amazing core technology out there, and the material science going into these it's fascinating. It's mind-blowing to me. And so looking at two gray boxes with a couple of fans and a plug in it, they are not the same. And I would really encourage you to challenge your engineering and your design teams. Are we looking at the best products available out there? It's not necessarily the most expensive ones, but there are HRVs that are in every format you can imagine, some with condensate drains, some with not. Susan and I were just at a conference last week. We found an HRV that has an ultrasonic element, and it vaporizes the condensate to blow out the exhaust. I can't believe that we're doing things like this, but it's so practical. The manufacturing advances and the availability of some of these components is really, really making these products sing now. So I want to move on to the zero carbon step code now that we've beat Teddy to death. As I mentioned before, this is very much a conversation about optimizing the use of fossil fuels and moving to electric means as primary. And I think just as a quick data reference, if we look at a breakdown of current emissions, or I guess 2017, not so current, but it's probably not very different today, emissions in the township, more than 3/4 of emissions are currently from residential and commercial buildings. And if you break those down by, what was the input fuel that resulted in those emissions, it's, what we expect. That big green 93% slice is natural gas. So this is because, again, on paper, the emission intensity of natural gas is 17 times what it is for electricity. So I can use 17 times as much electricity, pound for pound, BTU for BTU, kilowatt hour for kilowatt hour, however you want to gauge it. If there was a piece of equipment that consumed electricity and consumed fossil fuel at exactly the same efficiency, I could use it 17 times harder with electric and result with the same amount of emissions as natural gas. So it just means that, you know, going to electrical, we don't have to be particularly sophisticated. Switching any system from gas to electric alternative, even if it's not for the full time of the year, even if it's only for 80% of hours in the year, it is really going to move the needle. And we don't have to get rid of natural gas completely, but I do think we need to consider relegating it to a peaking or a standby role. So when it comes to meeting the higher emission levels of the zero carbon step code, efficiency of the system is actually its secondary importance. So you can have an ultra efficient gas system and it will still produce substantially more emissions than an electric baseboard. Let's see. So this dynamic of the zero carbon step code is where the tension really arises between higher building performance and the demands that we're putting on the electrical utility. So I'm starting to segue towards our EV conversation and the implications this has on hydro servicing for our sites. And the caution here is that a brute force electrification strategy, it might do wonders for reducing your greenhouse gas emissions, but it has potentially very significant knock-on effects on the cost and complexity of bringing our hydro service into these new buildings. So of course, next slide, if the move is to migrate our heating systems towards an electric first means, but reduce the amount of electricity that we're using, then I think heat pumps are an obvious part of the equation. While electric baseboards and electric hot water tanks are remarkably simple and they're very reliable and they're easy to maintain, or they hardly require any maintenance, to me, those technologies, electric resistance heating, that's what represents brute force approach to electrification. So I have seen many projects apply electric boilers out of the principle of we don't want to use any natural gas. If you are in a neighborhood that has a huge circuit and lots of capacity and it's not an issue, then sure, fill your boots, go for an electric boiler. But electric boilers are resistance technology. There's a time and a place to use them. There are some projects that have no choice but to use electric boilers, but that to me is like, that's the perfect use case for where we can still apply what are now very advanced and very cost-effective natural gas boilers. We use them for peaking. We use them to complement and back up heat pump technology. Another point I want to make here is that I don't think we can paint all heat pumps with one brush. And the reason I put these different heat pumps up here, this is just like a quick sample of the products out there that are kind of at my fingertips that I would specify for new projects. They're like cars, just like we have Teslas, we have Rivians, we have Volkswagens, we have Ford F-150s. All heat pumps come in different shapes and sizes, and the right one to drive your kids to school is not the right one to take a road trip. You know, it might be, you might find one if you've designed your building that way, but we have through the wall heat pumps, right? That Innova system on the right-hand side. We have multi-split VRF systems. We have these packaged kind of applied products that are air to water heat pumps that require a whole hydronic system. And, you know, is it 2-pipe? Is it 4-pipe? But really, it's a zoo of heat pumps. There's just all sorts of different animals. And it's really, really important to pick the right one. And again, I would say, go and challenge your engineering and design teams and make sure that you are really vetting what you're getting when you say heat pump. Don't just throw it away. It's a category. I don't know how it works. There are changing refrigerant technologies. There are different operating temperature regimes. They have different space and different maintenance requirements. Susan was alluding to, you know, are we bolting these on the side of buildings? Are we putting on the roof? It is a different space requirement than we're used to when we buried a piece of gas equipment, you know, in a boiler room in the basement or in a penthouse on the roof. These things often need access to outside. They're not immensely heavy, but they don't weigh nothing. So we need to tell our structural friends about them. And they're all different. So I would say, I think coastal BC, and I would still count Langley in coastal BC, it's prime for heat pumps. It doesn't get that cold. We hear lots of grievances about, oh, heat pumps stop working at -15. We have so few hours in this climate zone that actually touch that zone. If we are applying our systems correctly and doing, you know, good due diligence in our engineering, I believe air source heat pumps are, if we're going to use them anywhere in Canada, we live in like the utopia for air source heat pumps. And then buildings where cooling was already being provided, if we were not already looking at those for the obvious candidates to apply heat pump heating, then we've done something terribly wrong, because a building with a chiller already has a massive electric driven compressor. It already has distributed maintenance. It already has a central plant. To not make that compressor a reversible one that can also do heating, to me is it's a lost opportunity. So we're seeing very often that in commercial buildings, especially, it's actually the peak cooling that is driving our service size. It's not the heat pump and heating mode because our building envelopes are getting so good. It's actually the cooling. And so if we already have chiller systems, we should be looking at applying reversible heat pumps. All right, we're going to shimmy along here. 2 more slides, and then I'll ask you some questions and wake everyone up. If anyone wants to check the score for me, you can put it in the chat. I had mentioned before heat pumps for hot water. So the reason I think this is really glossed over, it's kind of benign to wash your hands with warm water. No one really thinks about the emissions associated with, doing their dishes and turning on the dishwasher, running the clothes washer, the laundry machine. But the reality is about 40% of total energy consumed by residential buildings in this province is for hot water. And it really comes from residential buildings. So I think there's a large subset of the audience on this call are probably in that residential sector. And we should be looking at this big slice of the pie, and is there a better way to crack that nut? The thing I love about applying heat pumps for hot water is we already tend to have centralized hot water systems that are outside of people's suites. So whether you're building a new building or whether you're doing a retrofit, we don't need to mess about in residential areas. There's no impact to ceiling heights, suite finishes, fixture types, noise in the units. None of that is affected like it is with heating and cooling and ventilation systems. This is stuff that's tucked away in a mechanical room or kind of relegated to the roof. And so switching this end use, domestic hot water production, from what has conventionally been de facto natural gas, this is, I believe, one of the most impactful ways we can reduce greenhouse gas emissions. And in some cases, I believe we can get to those higher steps of the zero carbon step code without doing that much more crazy stuff on heating and ventilation side. Just to mention what some of these pictures are. So the product on the left-hand side is the Sand and Sanco unit. This is a little CO2 heat pump that's built for residential applications. I've been going to this like meat and potatoes for every townhouse, single-family home, custom home that I've touched. It is quiet, it acts like a split system, and there is no on-site refrigeration connection. You don't need to hire a refrigeration tech for this. Your plumber can install it because it's just water piping to the outdoor unit. Works beautifully. Have had it in a passive house in Langford here on the island for about almost 10 years. Zero complaints, very, very robust system. And then coming to market, very credible international manufacturers in Mitsubishi and in Watts are producing these commercial and institutional sized air source heat pumps, also based on CO2. So without going into a master class on CO2 heat pumps, these types of heat pumps are very good at one thing, generating domestic hot water. They work great at high lift. They are not good at doing radiant heating. They're not doing it good at ventilation and heating. They're not good at really doing anything else, but they are so efficient and so reliable at domestic hot water production. I really think that this is going to be a huge trend for all buildings of all sizes over the next 5 to 10 years. Okay,
if I can
so
jump in on that, Andy, really quickly
yeah,
too.
please.
I was super happy to see you add this particular content on the presentation, because this was also very much aligned with the study that we did and some of the findings we had for some of the peak loads. And so now this is modeling based, so it does use sort of certain assumptions for occupancy and this kind of thing. But one of the things we saw was that, in the morning, there are a lot of heating loads that really cause electricity to spike. One of them being domestic hot water. A lot of people are showering in the morning, waking up, cooking, doing something to that effect. At the same time, the office buildings are starting up and coming out of their overnight setback temperatures. And so that was a time that we were noticing a fair amount of demand. And so if we can shift some of those loads or address some of those, that's always a good thing. And the other thing, I thought I had another thought, but anyways, that was the main one. So I'll leave it at that and let you finish your final
Susan,
slide.
you triggered another thought for me. I don't have a slide on this, so maybe you have to use your imagination a little bit. If I can go a little level deeper on heat pump water heating. something else that I've learned in applying these systems and speaking directly on this topic in other venues, I think we need to stop thinking about hot water as this instantaneous thing. It was very fashionable for a long time for people to call gas water heaters like instant water heaters or tankless water heaters. Frankly, it was very, very good marketing. But if it generates, hot water instantly, but it's like 120 feet away, like you're still waiting for 45 seconds at your faucet, so it's not instant. Anyway, I think we need to stop thinking about these as like instantaneous systems because really they're a battery. And one of the kind of design implications of going to heat pump water heating is it helps these heat pumps to work with a large volume of storage. And I mentioned that in this presentation because this is actually a strategy that we can use to reduce impact on peak electrical demand as well. So if you think about your storage tank as like this big battery of hot water that's ready to go. If you have a shower at 6 in the morning and you throw your kids in the bath at 6 p.m. at night, there's kind of 12 hours where you're not at anything close to peak hot water demand, and that's the time where you're charging the battery. So you can kind of exhaust the whole battery. You can drain it down, you can take all the hot water out of it, it'll fill up with cold again, and it'll take some time to charge up. The more volume you have, the more liberty you have to draw off that peak demand. And then the slower and the more lenient you can be with how quickly the system restores that. And there's this really interesting case study I heard, same conference that we were at last week, about a trial for an apartment retrofit in Vancouver, where they were switching their gas heat pumps their gas water heaters to heat pump water heaters. And Hydro actually incentivized them and said, you did the sizing, throw 2 more tanks on it. We just want to see what happens. And so they intentionally oversized the storage volume, got an incentive from BC Hydro, and Hydro in exchange said, in this trial, we'd like the option to turn off your heat pump water heaters selectively when we're approaching peak load. Because we know we have this extra kind of margin of stored hot water ready to go, no one's going to notice because it's going to take an extra couple hours of demand for us to draw that hot water off. And in the meantime, we can go send that capacity to do something else that's more important instead of keeping these batteries warm in the garage when no one's taking a shower. So I think that really unlocks like the dynamic nature of these systems. And that might not be the right solution for every project. I know space is such a constraint with these kinds of systems already, but it was a very interesting thing to think about. So final slide before we go back to some poll questions. I just want to re-emphasize, that zero carbon step code compliance does not mean it's an outright ban on natural gas. I do still think that natural gas has a very, very important role in most buildings for peaking and backup. I wish we had time for me to go and show you some fancy graphs and things on how to right-size heat pumps and how much we are oversizing these systems when you design it for the coldest day. But I will say, design it for, 3 degrees warmer than the coldest day, and throw a boiler at the rest of it, because you're going to just sip gas for a very small fraction of the year, and you're going to get that benefit of a right-sized heat pump working at its prime capacity without oversizing the system, and without paying out the nose for something that's going to be sitting there in standby for 97% of the year. So I think hybrid systems are a very important ingredient. Yeah.
If I can jump in there for a second.
Is that Jeff? Yeah.
To your point about the backup boiler, when there is that mentality to just no gas whatsoever, that boiler might be on, minor amounts of the year, like you said, but you're now sizing your electrical service to the building to support the potential that boiler's on. So that has a huge impact to the hydro service you're providing, all the distribution, the cost of that, and might be something that's very minimal. And like you said, in the end, if you've gone with a gas boiler or something instead, that's spitting out small amounts of gas and putting a lot of extra costs in for very little gain.
Yeah, definitely. Yeah, and what you mean is if we went for an electric boiler, the
Correct.
Electric resistance boiler has huge hydro implication because that switches on the coldest day of the year, takes over all the load from the heat pump. The gas boiler does not, right? And so in buildings where I had gas for a fireplace in the residential area, a CRU that has a coffee shop or a commercial kitchen, if I've already got gas service to the lot, and if I already can put a small meter on there, it's really not a big deal to use that gas boiler again for that peaking role. And thank you, Jeff, for chiming in, because the objective of that is to make it easier on our electrical friends and on the utility.
Andy,
okay. Yes.
We have a question I think might be pertinent to respond to right now, just about how much heat loss could be does one get with domestic hot water storage, and how important is that factor? Can you just speak to that really quickly before we move on to the next topic?
Yeah. I'm just looking at the question.
This one's from Nicholas Heap. This is there's a whole variety and
Heat
some
loss
agreement
from
that
domestic hot water
domestic hot
storage.
water
Yeah.
storage makes a
It's
great
very
battery,
important.
but
It's very important. We have seen buildings where the heat loss associated with the standby tank losses in the mechanical room, but more importantly from the distribution piping on a recirculation system, is equal to the demand for the hot water itself. So when you meter a system, you might see something like, okay, people consume something between 5 and 15 gallons per day of domestic hot water. Lots of things we could say about that assumption. And when we translate that to actual like power consumption at the hot water generation plant, that obviously drives the sizing. But then when we look at it in a dynamic basis, if we measure that hourly over a period of months or even a year, we will see that the losses coming through the insulation off that recirculating pipe, as well as those tanks sitting in the mechanical room, actually equal the amount of energy input to the tank just to make up for that standby. So that's not to say that's a bad thing on hot water tanks or on heat pump hot water. Sure, if we switched our hot water plants from gas-based to heat pump-based, yes, my recommendation is you need more storage. And so naturally, more cylinders of hot water sitting there in a mechanical room, there's going to be more heat loss coming off those jackets. But really, I think that the big lever here is properly designing our domestic hot water recirculation systems. If we can get our building designs to optimize the path of that piping, if we can get back-to-back washrooms or washrooms on the backside of kitchens or kind of a plumbing core that goes up the building, it will make a huge difference to standby losses and overall energy performance. But you know what? It makes an enormous difference on cost. And the number of plumbers that come to me and say, like, Andy, why do we have 4 hot water risers through this tower? If we had flipped these washrooms 180 degrees, we could have cut it in half. And so when we're pursuing electrification and higher steps of the step codes alongside this affordability crisis, I think we need to keep both of those things in mind. And there's actually synergies here. Going more efficient doesn't always mean more expensive. There are some design methods that we can embrace that actually do both. They make it cheaper to build and they make it more efficient. But it's a great question.
Awesome. And you can see I've activated the poll, and I think you're converting some people. It looks like a lot of folks are interested in in higher performance HRVs. Maybe we need to do a little bit more sessions on some of those domestic hot water heat pumps. But yeah, you can see some interest in uptake of some of these technologies, which is great.
Nice. Thank you for that engagement, everyone. And I had one more mechanical question after this one. I'm not sure if the poll makes it so we exit a question 4 before we flip it to question 5.
It does. I'll give people a 3, 2, 1, and then we'll flip over. Oops, sorry. There we go. So we're on to the
So the
last
first one was
there.
about possibilities, right? Question 4 was, what can you see in your future for adopting some of these recommendations and strategies? Question 5 is, what's going to be hard about it? So I'm seeing lots of responses for all of them, but some of them that are kind of floating to the top: finding qualified trades to install and commission, finding skilled design teams that can implement these cost effectively, increase space demands. I think that's very real for sure. And then, procurement, operations and maintenance, definitely depending on what kind of system you're looking at, what kind of building you're looking at. Yeah, those are real challenges. Okay, thank you for the engagement on that, everyone. Maybe we'll leave that polling question out. We can come back to it if we have time. But Susan, I'll hand it back to you on capital costs.
Yeah, thanks, Andy. And I think a lot of the information that you've been providing has been really leading to the question about costs. And one thing I just really wanted to share up front for this particular study, like I said, we worked with a professional quantity surveyor who reached out to a number of suppliers and installers to get capital costs, including installation for the study. But one interesting finding that came back across a couple of manufacturers and had a lot to do with what Andy's just been talking about, the cost of mechanical systems with different fuel types, is that we were finding that for makeup air units for quarter pressurization, and also for central boilers, so both heating and domestic hot water, excuse me, the electric units and their installation was coming back cheaper than natural gas. So that had some pertaining to the, that pertains to the findings that we were kind of teasing out of the study in the end. Now, obviously, because we were simulating so many different building types, we didn't look at whether the site, this sort of archetype site we were talking about, could handle service, a variety, which service connection size it could handle. And so obviously if a larger BC Hydro connection was required, sorry, I just need a moment there. So if the natural gas option were to allow for a lower service connection, then there's a huge capital cost there, but that wasn't part of the study. This was just for the equipment purchase and installation. So we have, before we get into our sharing our costing findings, we actually wanted to get a sense of what everybody's gut feel is now based on the information we've presented. What's your gut feel? Just answer quickly. What do you think is going to cost more? Reaching the upper tiers of the energy step code, upper tiers of the zero carbon step code? Does anyone think that maybe they're around parity? And I can see we have a few folks here who you know, aren't willing to hazard a guess, which is totally fine. Energy step code is definitely taking the lead. Upper tiers, yeah. Okay, I'm gonna leave that one open for another few seconds as we share our findings, although I think that's gonna impact the voting as we as we go to the next slide. So interestingly, we found the opposite of what the gut feel was. And we honestly were thinking the same, you know, envelope measures, those are going to cost more, walls, windows, more than HVAC systems. But as we were looking across the various archetypes, sorry, rejig there. Yes, we were in line with everybody's guess that energy step code was going to cost more than the zero carbon step code. And I think there were a lot of fears around the zero carbon step code add-on, that this is going to be causing fuel switching and is going to result in a lot higher costs. But what we were finding is that in order to achieve the electrification or to achieve the lower loads for step 4, we were going to need domestic hot water electrification to start with, which is what Andy was just talking about. And that basically brought us to where we need to be for the zero carbon step code regardless. So you can see here the results for the lowest cost option for the mid-rise, high-rise, office and retail, achieving the upper energy steps versus the upper zero carbon steps. And clearly for the energy steps, it was higher than for the zero carbon steps. So this kind of begs the question, we've had people say, can we just forget about energy step code and move to the zero carbon step code, because we're really focused on zero carbon step code reductions. Those are the cheaper things that we need to do. Is there a way we can just take the energy step code out of it? And one of the things we really looked at is that, you know, energy step code is still really important to reduce the pie before we apply the electrical loads. And this kind of leads us into our next topic and the importance of making sure that our buildings are designed efficiently so that then once we serve it with the electrical and any gas backup or peak loads that we might need, we're not overloading any aspects of our grid. So I'm handing that one back to Andy. Yeah.
Yeah. Just trying to acknowledge some comments in there. Really great discussion, everyone. Thank you for the engagement. Okay, so this is where I get to tongue-in-cheek qualify. I am a mechanical engineer, but I have in my past life overseen multidisciplinary teams for more than 10 years. And I will tell you the trade-offs constantly between mechanical and electrical are very real. So I'm going to do my best to cover these slides, but we do have an expert waiting in the wings here in Jeff at AES. So Jeff, feel free to chime in here if I put my foot in my mouth or if you have anything to add. We can answer questions as we go.
Sure.
So as I've emphasized a few times, the energy step code is about reducing thermal demand. And in general, I could say higher steps of the energy step code, yes, hypothetically, they should reduce peak electricity because peak electrical demand is proportional to the draw of the building for thermal energy, right? So if we have an electric building, less demand for energy means less electricity. But the same is not true for the zero carbon step code. Although emissions reduce with lower demand for energy as well, because the greenhouse gas emission intensity is so different between natural gas and electricity, the longest lever really is, am I primary electric or am I primary gas? And that's really the question that comes in here. And I think that's where we need to be thinking in terms of achieving these higher steps at the same time as respecting the finite kind of instant peak capacity that we have from our electrical utility. So next slide. I'm not going to pretend I can speak electrical here, but I will tell you I'm very used to the first questions at project kickoff meetings. Do we need a PMT? Will there be a substation? How big will it be? Can it go here? Does it have to have access to the property line? Does our lot even have sufficient capacity in this neighborhood on the BC Hydro circuit off-site, or will doing this project trigger a very costly and major utility upgrade? These are all very real concerns, and they are coming up on every single project, no matter the size, no matter the building type. And when we are looking at also making these buildings comply with the higher energy code steps and the higher zero carbon steps, these processes with the utility, they don't change as we're driving for those higher levels of performance, but they become something more and more important for us to keep in mind and ask early.
And
something,
yeah, go ahead. You go ahead.
This is a good spot, Jeff, because I'm going to move to EVs on the next slide.
Sure. Okay. Just want to note that as these loads are increasing on the electrical side from electrification of mechanical systems or EV charging, obviously that significantly impacts the electrical service. So BC Hydro, the most you can get is 1600 amps at 600 volts, which is more than enough to service a typical building. And I'm sorry, I should go back there. That's the most that BC Hydro will support on one of their own transformers. So for a typical project, I think the goal would be to have a BC Hydro transformer there supporting it. It's less maintenance in the future. If you're going to exceed that threshold, then you're getting into a private substation, in which case it becomes an owner's cost to purchase and maintain. So basically, as much power as you need is available. It's a matter of whether you can qualify for a BC Hydro service or you hit that threshold and you have to go for a private service. But overall, the application process for BC Hydro, permitting, anything like that, none of that is really impacted by this. They can supply it. It's just, but you do want to be engaging them early because it does take a while to get all of this through BC Hydro.
Terrific, Jeff. I'm very glad you stood in there. Okay, now I will flip over to EVs. With all of the kind of foregoing in mind, building performance, higher steps, electrification of our systems, limitations and implications for how we size our building peaks. How do electric vehicles play into this? Well, first, a few facts. So the Township of Langley, my understanding is different parking requirements per building type. They're on here, I won't read them. And currently, I believe there's no mandate for EV charger requirements for commercial buildings. And Annie, Jean, Kevin, chime in here if you want to interject with anything, but I think it's being considered. And so part of the study here was, answering an important question: what would the impact be of making a certain percentage of these parking requirements, the number of stalls on new projects, be EV ready, quote unquote EV ready? So to put things in perspective, we have an example here. Susan alluded to it when we were kind of introducing the study. We took that commercial building. So if we can go to the next slide, Susan. To put things into perspective, if we took that 6,000 square foot example office building and we applied the current zoning requirements that would apply in Langley, it would mandate 174 parking stalls based on floor area. And we looked at what would the implication be if we applied a 45% EV ready policy. And before I mean, the punchline's on the screen, but Kevin, you should chime in here because I think this is important.
Yeah, so thanks, Andy. And just to confirm or clarify, we are interested in impacts and really the technical responses of what these kind of charging requirements could place on buildings. It's not necessarily that we are considering a requirement. We just want to know what's on the table. Should we kind of move forward with examining EV charging in non-residential buildings? We do have charging for residential buildings, and that seems to be going successful for us. But just to confirm, just for phrasing's sake, that it's kind of a think tank analysis right now at this point.
Thank you. Great clarification, Kevin. Appreciate that.
And we did look at the 10, 25%, and 45%, but this is the kind of most extreme 45% result that we're sharing, basically, from that analysis.
And Susan, thanks for highlighting that as well. The tiers or the kind of buckets, in this case 45%, these were kind of directed by some kind of best practice charging requirements, kind of going out to the future of where some academics thinks we may be going. Whatever the township does consider, or if it does in the future, it will be based off of kind of consultation with our folks here in our region, based off of statistics that are really serving our residents and communities.
Yeah, great point. So I think important clarifications. I'm not advocating for a specific threshold. We're just trying to put in perspective one number, and you can prorate it in your mind, how it relates to the building load overall. So, okay, by now you've had a chance to review the numbers on the screen. 45% hypothetical would result in just under 80 EV ready stalls. And on a very, I've used the term brute force a few times, on a very conservative assumption, if that meant a single level 2 charger for each of those single stalls, that would equate to a 525 kilowatt demand just for those EVs. And if we compare that to, again, that hypothetical modeled office building, the whole rest of the building, heating system, ventilation, HRV fans, lights, plugs, everything else, only comes out to a 170 kilowatt peak, almost exactly a third, right? So we're at a 3-to-1 from EV charging demand to building peak for everything else for a modeled step 3 office building. And that is scary. To me, that means, EVs are absolutely an elephant in the room. We're talking about, we should go from 60 to 80% HRVs, or we should be looking at, CO2 hot water plants. But when we have a 3-to-1 implication on what does it mean to put what we used to get on the corner from Petro-Canada and bury it in the guts of these buildings, that is a different end use. It's not a building end use, it's a transportation end use. And the implications on servicing these buildings very significant. So important distinctions here. This comparison, again, it's kind of napkin math. We are comparing EV peaks. So is it realistic to expect that 100% of those EV stalls are all drawing peak simultaneously? We might imagine, rush hour is just finished and in 15 years, everyone has an EV and they're all charging simultaneously. I don't know. I think it's a bit unlikely, but hypothetically, that's a peak draw. And we're comparing it against, an orange. It's an apple to an orange. That 170 kilowatt building demand is a peak of many different end uses that are that are fluctuating throughout the day, right? So we're not, for example, including the chiller running at full cooling capacity at the same time as our, our heating plant running at full capacity. Those things would never run at the same time. And so we're looking at, yes, plugs and lights and heating and ventilation and all these other things. We're chopping kind of a dynamic peak through that. Kevin, you have another clarification.
Yeah, just a comment, and I think this was for level 2 charging, right? So whatever it is, 40 amp or something like that, at some maximum amount, and the calculations here are done in a scenario which may never happen or might not for a long time. Also want to highlight that as this is being examined across the province, there's probably 100 different ways to slice this pie. Where that could happen, it's probably not likely in a lot of regulation moving forward where they'd offer full power to, say, in this case, 45% of spots. It's probably going to be 10% of spots are going to have X amount of maybe level 3, a certain amount will have a level 2, and a certain amount will have different types of charging. So as we examine this, and I'm highlighting this as a think tank, as an examination of just what could be possible, where power numbers come out shocking. And I think I premised the talk way early, maybe around 9 o'clock, that we're going to see some shocking things, some interesting data. It also then informs folks like us that, okay, so how do we mitigate, and how do we make policy that's a little bit more sensible for our buildings and our grid. So I appreciate that this is a shocking number, so to speak, pun intended, I guess. But we are aware of what that means, and we will then, of course, take that back and put our pencils to paper and see how we can mitigate.
Great. Yeah, very important qualification, Kevin. Thanks for that. And I see it the same way. This is not a realistic example. We're just trying to put in perspective an extreme, because the next slide, Susan, is there is a very strong case to mitigate this. It's unnecessary to plan for these simultaneous peaks. It is an improbable, impractical peak to accommodate. You don't drive to Petro-Canada and expect to fuel 80 cars at once, So why do we expect the same from EV facilities? So I think I've already addressed, the 170 kilowatt building load being a dynamic peak versus the 525 being a worst case instantaneous peak for EVs. It's an apple and an orange. And this is where I get to disclaim again my qualification as a mechanical engineer. I think we really need to look at what is the definition of EV ready. It doesn't necessarily mean you plug in to a level 2 and you get it right away. And so my understanding, BC Hydro's definition of EV ready is just that there's a parking space that features an adjacent energized electrical outlet. And it doesn't mean it's one outlet, and doesn't mean it's one charger for every single stall. So could there be creative ways of solving this where you have access to a charger for, a number of adjacent stalls? And, all of the architects on this call know what it takes to optimize a parking layout for sure. But could we look at putting these on spikes so that there are potentially 4 or even 6 stalls that can be served by the same charger? And we are enabling those stalls to have access to EV, but they don't all need to fuel at the same time. Jeff appropriately has his hand up to save me here, and I see some questions coming up. So go for it, Jeff.
Yeah, so what I was just going to note is that typically for these kind of buildings, like that worst case scenario that Andy is talking about is essentially allowing a car to charge from 0 to 100% over the course of a workday. That's probably not a realistic case, and maybe not something that we want to be allowing for here. What we typically do is the sample in these calculations were for 40 amp chargers. We typically actually share that between up to 4 stalls, 3 to 4 stalls. So what these chargers can do is, if one car is parked there and plugged into that charger that's spread over 4 circuits, over 4 stalls, that will get 100% of the power. 2 cars pull up, they're each going to get 50%. 4 cars pull up, they're each going to get 25%. So that's a way that, automatically there you can divide that demand by 4 there, and significantly reduce that load while still having that flexibility as well.
Kevin, go ahead.
So on this matter, so the Township of Langley recognized way back in 2019 or so, when we were looking at EV adoption for residential buildings, that this would be a challenge. So we do permit the use of energy management systems, and provided a bulletin or a set of guidelines on how to design that. And exactly to your point, Jeff, we have certain tiers of how many amps you're offering and how many times we can split it for that kind of more managed managed distribution. So we would imagine that in the case of office buildings, it would be probably a similar type of usage where employees are tied into the energy management system and they could charge kind of throughout the day rather than all instantaneously. And when we did release that was in 2019. We released the bulletin before it was active. And we didn't know what was going to happen, but we thought this is probably the way of the future. Every single building, maybe minus one, residential building, a Part 3 building that we've had since 2019 does use an EMS. So it's clearly a winning strategy for our development.
Great, thanks. Okay, I only have one more slide. I think we're on the home stretch here, and then we can flip over to Q&A for the balance of our time. So zooming out, just again for perspective, from a province-wide utility view, BC Hydro's projections don't seem to be in a panic about a huge problem due to EVs, but at this scale, they're looking at total consumption on a grid scale. They're not looking at peak demand at individual building connections. So suffice to say, to bring kind of the whole M&E piece together, electrifying our buildings alongside integrating power for our evolving transportation needs, it's a very nuanced subject, you can see. It's important to see that brute forcing our way out of this problem is, maybe technically possible, but likely not practical and not affordable. And these are all, tensions that need to be balanced as we're pushing the performance of our buildings. So a thoughtful approach to moving our mechanical systems towards electric primary means at the same time as intelligently accommodating EVs. These are two parts of one equation. I think we're all fighting the same fight here, but we need to, we need to work together and manage some of these tensions instead of just, going back to the same solutions as yesterday or taking, off-the-shelf solutions and plugging them in, but not at the right size or not at the right kind of purpose. So appreciate the chance to speak with you all. I look for questions. I'll hand it back to Susan to bring it home.
Thanks, Andy, and everyone for jumping in as well in the electrical conversation. We may have more questions we want to address in that during the Q&A. So just as we wrap things up, we've got a summary slide here that outlines a lot of the anticipated design impacts that we might see, and also some of the lower cost ones that that came out of this study for folks to consider in order to meet these upper step code projects. So the basic things we were talking about again were the simpler form and lower window to wall ratio, considering how to manage both overheating at the same time as efficiently delivering both heating and cooling to our buildings for both space conditioning and also domestic hot water heating. Looking at electrification of those systems throughout the year with some peak load as necessary for that can still be natural gas and other to keep our greenhouse gas emissions low, and then considering some sort of time of day energy use both for the building side of things and EV management. So we'll pop the last question up there to the group. This one's a little different in that you can actually add your own response. So type in a response. We're just looking for interest in whether there's other topics people are interested in hearing more detail on. And we can also use that as a prompt for something we can address through the Q&A, although I think we've actually got a lot of great questions we can still look at in the chat. You can also upvote or other people's questions if you like what they're saying, and so you don't have to repeat the same thing twice. I did notice one initial question just to kick off the Q&A that maybe Jeff might want to look to. I think this was in response to your comment about how BC Hydro can provide a transformer up to 1600 amps. And then someone has asked here, due to the EV charging requirements from the city, they might need to request a unit substation. Would you recommend anything in this case?
So sorry, I'm not sure what the recommendation is. Like, so if they exceed that 1600 amps, 600 volt, just to clarify, you can get a 208 volt service at 1600 amps, or you can also go up to 1600 amps at 600 volts. So that 600 volt one's about 3 times the capacity. But if you were to exceed that and needed a unit sub, still the same process that you're going through BC Hydro, but it's you're coordinating a high voltage service with them rather than a secondary voltage service. And then you're needing to accommodate that added equipment on site, either with an exterior mounted unit substation, or often these are mounted indoors So needing a much larger electrical room to accommodate this equipment. I'm not sure if that answers the question or if that could be clarified at all.
Thanks, Jeff. Great. Andy, do you have a question? Do you see a question on there, either in the ones people are voting on or on the chat that you want to pick up and address?
Well, I was looking at the chat. Let me look at the poll here. How do we improve the invasion of unsightly heat pumps? That's a good one. Alternative solutions for building envelope and energy modeling. That's contentious. I might leave that one to you, Susan.
Alternative solutions to envelope and energy modeling. I mean, I think I would, maybe this is a bit tongue in cheek, but if I think of the history of energy modeling, which I've kind of been involved in over the last 20 plus years, it really came from, you know, initially we had code requirements do this. And then it kind of merged to, well, actually, I can put in a cheaper mechanical system if I spend more money on my windows and walls, but we have to assess that. And so there are other methods, right, to achieve higher performance if we have sort of more prescriptive requirements. But I think that the modeling and the honestly, the step code modeling, it's kind of the easiest type that there is out there these days. And it's consistent across the province, which I really appreciate as someone who's been modeling for 2 decades. It used to be, it still is complex. We call it code spaghetti a whole lot of, you know, you start with a step code, but then there's underlying NECB, and the more strings that you pull on, you pull all these other codes out of the weeds. But even so, it's one of the most straightforward modeling approaches right now that allows designers to be flexible. And that kind of goes back to Andy's point earlier about it's not a one size fits all solution on how to get there. We're really looking at model for your building so that you can assess what is going to be the cheapest, the most cost effective for this project on this site to get to those tiers. But anyways, I am obviously coming at it from a certain biased perspective.
I might tack on to that really quickly. Susan and I are familiar with an interesting case from another jurisdiction, not Langley, where there was a private developer making a case to exempt strip mall archetypes from the TEDI requirement because they naturally have a very poor form factor. They have a lot of building envelope and not a lot of floor area. And so is it realistic or is it economical to apply, you know, step 3 or even a step 3 commercial TEDI limit to a project that's really not conducive? You know, should we be putting triple pane glass on strip malls was kind of the philosophical question. I don't personally have an answer to that. I think it's a really fascinating trade-off, and I think that's part of the reason why the zero carbon step code was implemented, because we are seeing, you know, in the poll and the costing survey both revealed, you know, the incremental cost for the higher levels of the energy step code is quite high, you know. And I saw another comment here about envelope upgrades having even higher embodied carbon. You know, is that the right thing to do to push our new buildings so high in terms of insulation and airtightness when we haven't really addressed the carbon issue, which is really what's moving the needle in terms of climate change? So that's kind of a philosophical spin on the energy modeling question. I just want to throw that in there, though, as it applies to alternative solutions. There has been conversation in the province, other parts, about, you know, should there be different compliance paths for those higher steps in certain kinds of buildings. I do want to touch on 2 other questions if we have time. So I saw one that is really interesting. It's got a lot of thumbs up, but I don't understand it. So if whoever put that one in there, maybe you could elaborate in the chat while I address the second one. But net zero homes and airtightness, what does that mean? Is that there's something you'd like to learn more about, or do you have a specific question? While you chew on that, I also wanted to tease out this piece. Our infrastructure heavily relies on natural gas for energy. I agree that's true at the moment. Have we considered the cost of overall electrical infrastructure upgrades to accommodate all this? And I think that's a really fascinating question to me, because depends who we is. I think the private sector has considered it, and I think we're really scared of it, and rightly so. I've heard lots of horror stories of developers kind of being first in that trigger a neighborhood upgrade, and then they kind of like eat the cost to make it easier for all of their neighbors and downstream developments over the next 10 years to come in. Jeff is probably better equipped to speak to that. I think Hydro has evolved their policy. I don't know. I think it's called a pioneer program or something like that. So where you see a neighborhood upgrade, you're not forcing the first developer to trigger it to eat 100% of the cost for the rest of the block. But I do think private industry sees it. I think Hydro is looking at it, but I'm not sure if there's like a central place where that conversation is really happening.
And I think right now the way we actually, I'm not, this it's possible there's a change, but basically the first one in pays for it, but then as new people join on, they start getting kind of credits back to eventually even things out.
Yeah.
Just jump in here. Thanks, Jeff and Andy, for raising that question. Fortunately, BC Hydro couldn't be here, but we have invited him in the past to start talking to, what's going on here around electrical load infrastructure. BC Hydro is putting in, and I'm just kind of going from memory. I'm not kind of speaking for them, but they are putting billions and billions of dollars into infrastructure, including here in Langley, to deal with electrical upgrades. And as well, they are dealing with, Andy, that problem where who wants to be the first in there. And as far as I know, their new programs are active for development, and they were meant to really, really, really alleviate some of those major concerns about you being the first in to bring all that power back and then getting basically paid back per development over time. I think they felt, or they heard that that's not really how industry wants to do it. So I can't speak too much to it, but there are resources out there. I do recommend you do get in contact with BC Hydro to get it straight from the horse's mouth. I do believe they really intended on solving those problems, Ed.
Thanks, all. And I can speak very briefly. I know we have like 1 minute left to the question about the wood frame and high-rise concrete incremental cost being roughly the same. And my answer is we have a little bit more detail of that in the report. I don't have all of the breakdown of it specifically to share right now, but it has to do with a number of different factors. So like the wood frame was starting with a different base cost because it's mid-rise MERV versus a high-rise. And then the window types that we were using for each individual wood frame versus concrete was different. The percent glazing was different because you don't usually get high rises with such a low percentage glazing. So there was a lot of different factors at play there, and they just both happened to work out to around the 3% mark incremental cost to get to step 4.
Susan, if I may just have a quick second. It looks like we're at 11 o'clock. I don't know if Susan or Andy or Jeff will take any more questions, but I just do want to highlight we do have a survey. Annie put it in the chat there, and you'll probably get an email when you get your credits to conduct the survey. Please do take 5 minutes to do the survey. This is how we know how we're doing, what you want to see, and really importantly, if we should continue doing these kinds of events. So do that survey. And thanks again for coming. I'll pass it back to Susan, Jeff, and Andy to answer any other questions and say goodbye.
Yeah, thank you so much, Kevin. And again, huge thanks to the Township of Langley for hosting this session, and to everyone for coming and participating. There has just been a fantastic level of chat in this. And I think we're going to have to loop back. So I did see someone ask earlier if the slides will be shared, and yes, we can send out PDFs of that. Someone also asked if the polls would be shared. I can see if we can embed that within the slides. I'm not 100% sure how that happens, but we'll do our best to share that with you, because yeah, that's great information for everyone. So yeah, thanks again. If you do want to follow up with us, please feel free to reach out. Be happy to chat further about some of these topics. And yeah, I hope everybody has a great rest of the week. Go Canada, go.
Thanks, everybody. See you guys next time.
Thanks, everyone.